I'm going to be briefly explaining most of the equations on Aston Martin's new Formula One car livery that will be used in the 2025 US Grand Prix. As you can see in the picture, the car looks stunning. To quote Aston Martin's website, the livery will take the normally invisible signs of a Formula One car and make it visible through design, which includes a series of F1 related scientific formulas. The concept aims to bring to life on track the innovations behind the partnership and shine a light on the talented people who work to make it possible. The equations are written on many different parts of the car. We will start on the side of the car. The first equation seems to be cut off, so I'm going to come back to that one. Next, we have the downforce equation. The downforce, F subscript down, created by the aerodynamic forces on the car, is equal to 1/2 times rho, the density of the fluid, which would be air for a Formula One car, times V, the speed of fluid in relation to the car, which is the speed of the car in this case, squared, times C subscript L, the non-dimensional coefficient of lift, times A, the frontal area of the car. The lift coefficient terminology comes from plane aerodynamics, but here the force is downward to generate more tire grip in the corners. For subsonic flow, which is when the speed of the fluid with respect to the body is less than the speed of sound, the lift coefficient depends on the geometry of the car and in general the Reynolds number, which can be seen as the ratio of inertial forces and viscous forces. The coefficient of lift is determined experimentally or using numerical simulations. To give an idea of the values, the lift coefficient is about 3 and the frontal area is about 1.5 meters squared for a Formula One car according to Aston Martin's website. Next, we have the drag force equation. It is very similar to the downforce equation, except the lift coefficient is simply replaced by the drag coefficient to calculate the drag force, which acts in the opposite direction as the car's velocity. The next equation is related to the volumetric efficiency in an internal combustion engine. But sorry, I'm going to skip this one because I'm not familiar with it. In the middle on the right, we have the Reynolds average Navier-Stokes momentum equation in vectorial form. Here they're using index notation. I would encourage you to read about index notation if it interests you, but essentially it is a more compact and precise way of writing vectorial equations using these indexes like I and J. Let's start with the regular Navier-Stokes momentum equation and come back to the Reynolds average part later. The Navier-Stokes equations are a set of 3 partial differential equations that govern fluid flow for Newtonian fluids. Here's the Navier-Stokes momentum equation for incompressible, meaning constant density flow. This is the second equation of the 3. The first term of the left-hand side of momentum equation is the derivative of u, the velocity, which is a vector, with respect to t time, and represents the local acceleration. The second term is the convective acceleration. The right side is the sum of pressure forces, which are calculated using the gradient of P, the pressure, and the viscous forces, which are calculated using the Laplacian operator applied on the velocity. Now, in turbulent flow, the velocity fluctuates, so we can break the velocity down into an average component and a fluctuating component. Inputting this decomposition into the Navier-Stokes momentum equation eventually gives the Reynolds average Navier-Stokes equations after many simplifications. The last term is nonlinear and is called the Reynolds stress. The Reynolds stress term makes it so that the equation requires turbulence models to close and solve the equation because there are too many unknowns. This equation can be used with turbulence models to simulate turbulent flows. Moving on. In the bottom left, we have the Arrhenius equation. The Arrhenius equation is an empirical relationship that is often used to determine the rate of chemical reactions or the energy of activation. This might be used to calculate the combustion reaction rate in the car's engine. The EXP means Euler's number, E, which is approximately equal to 2.72, to the power of whatever is in the brackets. So the Arrhenius equation can be written like this. K is the reaction rate, A is a Prix exponential factor, EA is the reaction activation energy, R is the universal gas constant, and T is the absolute temperature measured in kelvins. Next, there is the equivalence ratio equation. Again, this would probably be used for the engine. It is a dimensionless parameter in combustion science that expresses the actual fuel to air ratio to the stoichiometric fuel to air ratio. If it is above 1, the real mixture has excess fuel compared to the theoretical ratio, and if it is below 1, the real mixture has excess air. Now, looking at another area on the side of the car near the cockpit, we can see the drag equation along with two other equations. The one in the middle is the thermal efficiency of fuel conversion. It is simply the ratio of the useful output power, P, and the available chemical power of the combustion reaction. Chemical power is the M fuel, the fuel mass flow rate, times LHV, the lower heating value, which is defined roughly as the amount of heat released when a fuel is combusted but has more conditions shown here. Next equation on the right here is probably the simplest on the list. It is simply the power, P, of a rotating body, where the Greek letter tau is the torque or moment, and omega is the angular velocity. Moving on to the front wing. In the middle here, we can see an energy balance equation. On the right side of this scalar equation is the work done by the engine by integrating F engine, the force produced by the engine, over the distance traveled by the car. The left side includes the kinetic energy, 1/2 times m, the mass of the car, times v, the magnitude of velocity of the car squared. The second term is the potential energy of the car. Mass times g, the local gravitational field of Earth, times h, the elevation or vertical position of the car with respect to an arbitrary reference point. The third term is an integral of the drag force over a distance to calculate the work done by the drag force. Finally, the fourth term is similar to the third, but for the rolling friction force of the tires. The work done by both the drag force and the rolling friction force are negative because these forces act in the opposite direction as the velocity of the car. In this form, this equation could be interpreted as the work done by the engine needed to accelerate the car from rest to a speed v with an elevation change h, while overcoming the energy losses caused by the drag force and the rolling friction force. Lastly, on the bottom, there is what looks to be a heat transfer rate balance equation. Though without further context, I do not want to try to explore further than that, as it would be speculation. There are also equations on the rear wing, but they have all already appeared in other places I discussed. Please let me know in the comments below if I made any mistakes. All of my references are in the description below. Finally, I want to mention that a few of the screenshots of equations are from the Aramco STEM challenge on Aston Martin's website. The challenge is a Formula One themed scientific quiz, and if you like science, engineering, and Formula One, I encourage you to try it. The link is in the description below.